the only slide I'm going to show you for a minute here. In chapter 9, they talk to you about the polarity of molecules, okay? So this is where you have to actually look at the Lewis structures and decide whether or not they're polar or nonpolar. Like overall, the whole molecule, not just the bond, okay? But in order to understand if they're polar or nonpolar, you have to understand if the bonds are polar or nonpolar because that factors into your decision, okay? I don't know. I'll look. I don't know probably isn't a very helpful response. 23-ish. So I'm actually not going to do much. I don't love this slide. I would have preferred a flow chart. There's too many questions and answers. I'm going to use the board, okay?
Are you going to draw a flow chart?
Yeah, let's draw a flow chart.
No, I'm going to draw molecules.
Oh.
And we're just going to practice. So we're going to take this for a little walk. Are you off camera?
Yep.
You are. Good. Wait. Just
Maybe
kidding.
Maybe
Good thing I'm recording while moving the thing. All right. So.
Just sneak over right in front of
Yeah, just cover that up. All right.
Wait, is it video taken out of the iPad or out of the phone?
iPad.
What would be the point of that?
Okay.
Well,
I
it has a
do
little
maybe
camera.
want a better. Hold on.
Camera.
I want better lighting, I think. Yeah.
Oh,
I'm sorry, but in order for our viewers at home to be able to see what we're doing.
This video is brought to you by viewers like you.
Yes, exactly. Outfit provided by. Oh no. All right. Anyway, are we listening? All right. We're gonna look at a few structures here. Okay. We're gonna start with F2, which I'm gonna make my dots a little darker. Okay. So here's F2, correct?
Yes.
All right. What did we say earlier about F2's bond? Polar or nonpolar?
Non-polar.
Is there pull or no pull?
No pull.
No pull. Identical twins. No pull, right? So nonpolar bond. If the molecule has nonpolar bonds, is there an area of this molecule that's more negative than any other area? No, therefore the whole molecule must also be
Negative.
no.
Neutral.
Nonpolar. Nonpolar molecule. Okay? So, look. You have to judge when you're looking at the molecule. Here's what you're looking for. Pay attention. You're analyzing the bonds. Are the bonds being pulled towards any one region of the molecule in such a way that one part of the molecule is significantly more negative than the other parts of the molecule? If so, then the molecule is probably okay. If there are more electrons around one area of the molecule is polar. If they're not being pulled significantly in one direction, then it's nonpolar. Okay? So you have to look at that. Right? So you look at the bonds and you look at the distribution of the electrons. Okay? So look at HF. Tell me about HF. Polar bond, polar molecule, what? Let's start with the bond. Polar bond. Which way are the electrons being pulled? Towards fluorine. So you make this little symbol, right? So that's a polar bond. Is this molecule polar or nonpolar? That's polar because this area here has all the electrons, doesn't it? So that's an uneven distribution of electrons. So that's a polar molecule. All right, now I'm going to draw CO2. Okay, I erased it earlier. So CO2 looks like this. Okay. Who has the better pull on those electrons? Oxygen has a much better pull on the electrons, right? You can look up the values if you want. Go ahead, look up the values. Somebody, go to that page or that slide. I think oxygen's like 3.5 and carbon's 2.5. Go ahead, look it up. Prove me wrong.
So would it be like that?
I'm right. Oxygen's 3.5. Carbon is 2.5. Okay? So the electrons are being pulled this way, right? And they're being pulled this way. Is there one region of the molecule that has the majority of the negatives?
No.
No, because they're being pulled in opposite directions, aren't they? So they're kind of balancing each other out. So those are polar bonds, but it's a nonpolar molecule because the electrons are being pulled symmetrically in opposite directions. Jacob, make sure Elizabeth can see around you. Okay, just checking. Take a minute and make sure that makes sense to you.
Makes sense. Like Stretch Armstrong.
Yeah, Stretch Armstrong, exactly. Do you understand? Like, no? Okay. Because it's a symmetrical molecule, your electrons are being pulled to the left and they're being pulled to the right. So there's not one area of the molecule that has like more electrons than the other. Okay? So it's balanced. Like if you think about it this way, like they're getting pulled here, they're getting pulled there. So those two regions are in opposite directions of each other, so they're kind of canceling out. Okay? Like if this is 1.0 to the left, this is 1.0 to the right. So you could think about it that way. That's nonpolar molecule. All right, now I'm going to draw water. Okay? Take a minute and think about water. Think about the bonds. Okay? Is the HO bond polar or nonpolar?
Polar.
Polar, very polar. Okay? Hydrogen is a 2.1, oxygen's a 3.5, so that's a very polar bond. Who has the pull on the electrons? Oxygen. So they're being pulled inwards towards oxygen. Okay, so polar bonds. Is the molecule polar or nonpolar?
Polar.
It is polar. Why?
Because there's
All the electrons are being pulled towards the middle, right? All the electrons are being pulled towards the middle. Here's a little thing just so you know. When we're looking at the electrons, we're looking at the dots too, okay? Anytime you have a central atom with an unshared pair or two, it's always a polar molecule. So anytime the central atom has unshared pairs on it, that molecule is always going to be polar. So the bent shape is always a polar molecule. Okay? Trigonal pyramidal, always a polar molecule because they all have dots. Okay? So polar bonds, polar molecule. All right, now we're going to do ammonia. Look at ammonia. Are the bonds polar or nonpolar?
polar.
Polar, because I think nitrogen's 3.0. Is that right? 3.0 and 2.1, so that's a pretty big difference. Okay. Now, those are polar bonds. Okay. Who's winning? Nitrogen. So where are all the electrons being pulled? Towards the center. And what does nitrogen have on it? An unshared pair. And what did I just say? Unshared pairs on the central atom always means polar molecule. Okay. We good? I have more to draw. Yes?
Well, can there ever be a nonpolar bond between two different elements?
Just wait. Yes. Okay. Next. We're going to do carbon tetrachloride. Take a minute. Think about the bonds. Think about the molecule. Okay? This one's a little tricky, so I'll give you a minute to think about it. Okay, draw it for yourself. Think about the bonds. Think about the molecule. What are the bonds? Polar, okay? Because carbon and chlorine have a big difference. So the bonds are polar. Who's winning the tug of war?
No one. Chlorine.
Somebody has to be winning. If it's a polar bond, somebody's winning. Chlorine's winning. Right? So all the electrons are being pulled towards chlorine. Polar or nonpolar molecule?
Non-polar.
Nonpolar, because these bonds are, like the pulling of these are canceling each other out, right? Okay, so nonpolar molecule. Again, I would say because it's symmetrical, okay?
Just negative on all sides.
Yeah, but like, so the negatives are kind of canceling each other out. There's not a negative area. Okay, here's one. Griffin, this goes back to your question. Okay. What are these bonds? Look up the numbers.
It's close. Where?
It is 0.4 of a difference. Why? Carbon's 2.5. Hydrogen is 2.1. Remember, we said the bigger the electronegativity difference, the more polar the bond, right?
Not very cool.
Very slightly polar. Barely polar. That's what I would say. Like, barely polar. Is carbon really winning this tug of war? No, not really. Like, you could make like a teeny tiny arrowhead if you want, saying that like carbon has a slightly better pull on those electrons, but does it really? No. So, barely polar bonds, what do you think? Non-polar. Because it's not really, the electrons are not consistently going anywhere, okay? What happens if I change one of these H's to a Cl? Oops. Now it's polar, isn't it? Okay, because now this is a very lopsided molecule, right? Does that make sense? Okay, did you have a question? Did you? Yeah.
So without knowing the numerical values, how are you supposed to know if it's a
Position on the periodic table.
Well, like some of it's funky around fluoride.
What do you mean?
Like it could be like it's 3.5 for oxygen, but 3 for chlorine. So like, and then it's like 2.5 for S. Or like,
So,
are you just supposed to memorize like?
no, you're not memorizing them. This is what I was saying. You're looking at the bonds like relative position-wise. So like the sample exercise we did where we were comparing multiple atoms, we weren't looking at it numerically. We were looking at it based on their positions on the periodic table, understanding which one's more polar than the other one. Okay? If for some reason they wanted you to have the values, they would give them to you. Okay? And then shape-wise, you're looking for symmetry, okay? And you're also looking at the bonds. If you have polar bonds, chances are it's going to be a polar molecule, assuming it's not completely symmetrical. Okay? If it's completely symmetrical, then it's going to be a nonpolar molecule because there is no pull in any one direction.
But like C to Cl is only a 0.5 difference, and H to C is a 0.4.
So here's the big thing though. These are like pulling oppositely.
Yeah, but like the actual bonds.
No, I understand what you're saying. I know. But the bottom line is this is a better tug of war player.
By only 0.1.
It's still a little bit of an improvement.
So it's 0.4 that cut off.
Keep in mind 3.0 compared to 2.5 versus 2.5 to 2.1. Like the bottom line is chlorine is a much better tug of war player than either of these. So we're not just like you're looking at the difference, but you're also looking at like who's involved. Like in general, chlorine's a better tug of war player. It has a higher number. Like those differences are coming from higher numbers.
Would chlorine and bromine still be polar? So that's 3 to 2.8.
It would be slightly, like not really. That would be a linear molecule. I would go with nonpolar.
So it does have to do with the numerical value.
And the symmetry. A chlorine bromine looks like this. Is any one of these pulling on it significantly better?
But aren't you just looking
I'm
at
asking.
what?
Is one of these a much better tug of war player than the other?
Not much better.
No. So therefore, is there a strongly negative region to this molecule?
No.
No, therefore it's nonpolar. Okay. All right. So does that clarify that? For most of you. Yes? All right. Then can we talk? Hold on. I want to do one more thing, and then we're going to be done. Okay. You're on camera. All right.